I think we should be fine. We will also be recording this talk, so whoever can't make it today can view it online later. So I see Akash has also joined. Okay, so we'll wait for another minute maybe, and then we'll
Sure.
start.
What is the expected time?
It's roughly an hour, including questions.
So the talk can stop at 4 points. Like,
Okay.
I encourage to ask questions actually. Like at one of the venues, I was barely able to make past 10 slides. So
Okay. Yeah. I think we'll have some number of questions. Um, and so is that Mukul who is at the CSE department?
Yes, yes.
Oh, okay.
Yes.
So you will be able to start the recording, right?
I have already
it
started
started.
recording.
Oh, it's already recording. Okay, so we'll trim it when we uh, put it online. Uh, okay, so then, without further ado, I will start. I will introduce. So, yeah, very, very happy to have Hemanta Maji today. And thanks also to Akash for organizing this, for inviting Maji. So Hemanta happens to be one of my, first students. Actually, it's my second student from way back. So he did his BTech at IIT Kanpur, right? And
Yes.
then a PhD at University of Illinois Urbana-Champaign and a postdoc at UCLA. And for the last few years, he has been a faculty member at Purdue University. And he has been doing a lot of very interesting things at the intersection of cryptography and various kinds of mathematical areas. So today he'll tell us about geometry and cryptography. So over to you, Maji.
Thank you, Manoj. Let me try to share. Um,
Yes.
so can everyone see my slides?
Yes, we can say it.
Okay. And can you see my cursor as well?
Yes, yes.
Okay. Yeah, then I will use my cursor in the talk. Today I will be talking about some connections that we have established between secure multi-party computation and geometry. And This is a joint work with my colleagues Saugato Basu and my students Hamid Raza and Hai. Hai has recently graduated and he's currently a postdoc with another professor here and looking for future postdocs. So today's talk will be roughly based on a paper that we wrote last year, Geometry of Secure Two-Party Computation, and some work that unpublished work that we have currently, and some other ongoing projects. So. So let me begin by giving a slight motivation as to why secure multi-party computation is important. It has numerous applications in social, scientific, commercial, and security domains. Um, it helps actors meet privacy expectations and regulation and comply to regulatory laws. So it is one of the premier technologies that is expected to bridge the data utility and privacy chasm. And secure multi-party computation is one such privacy preserving and enhancing technology. To achieve the security guarantees, it uses it incurs some overheads like some computation overhead, network communication overhead, randomness overheads, and other cryptographic overheads. And using these extra resources, it is able to achieve some notion of security. So this overhead of security is a significant obstacle to its adoption, and our research aim is basically to reduce this overhead of secure multi-party computation, or MPC. So let me give a quick summary of what to expect from today's talk. So we are looking at, we are studying the feasibility and optimization of secure multi-party computation with respect to their communication and round complexity. This problem was open since 1989, and the main solution methodology that we have developed is known as geometry of secure computation. It's essentially a wormhole that connects cryptographic research with geometry research, and we will see that it actually leads to fascinating new research problems in state-of-the-art geometry research. And our main technical contribution is the introduction of something we call as generalized convex hull. Obviously, as the name suggests, it's generalization of the typical notion of convex hull that we have, and this leads to new research direction in geometry research. And finally, this technique has automated the search and design of secure multi-party computation protocols. The way I like to put it is that secure multi-party computation protocol design is no longer limited by human ingenuity and intuition. We have been successfully able to convert some forms of secure multi-party computation design problems as combinatorial optimization problems, and we can throw computational power at it and directly search for the optimal protocol that we want to find. Additionally, it also automates obstruction detection. What I mean by obstruction is obstruction to achieving security within budgeted resources. Typically, the way this research is performed is lots of smart folks come up with invariants which are preserved during the execution of a secure protocol, and they try to show that under these invariants, certain notion of security is difficult to achieve within budgeted resources. However, as we will see, our formulation of the problem makes it significantly automates this process, and it's as simple as testing whether a point lies outside a set or not. So it is automated obstruction detection that we are proposing. Sorry. I must remind everyone that this talk is in the setting of information theoretic cryptography. So for all purposes today, there are no one-way functions. There are no one-way functions. Every easy to compute function is easy to invert. There is no fully homomorphic encryption. The best way to imagine is that a one-time pad is secure. That still remains in that still continues to be secure in information theoretic cryptography. Any questions at this point regarding what do we mean by information theoretic cryptography or anything? Okay, so next, since I promised you that we introduced a new notion of a generalized convex hull, so let me just introduce it at the outset. To introduce that problem, let me first give a new perspective. It's not new. It's it's a helpful perspective on convex hulls. So suppose we have these 4 points. We will call them initial points in 2 dimensions. And our objective is to compute the convex hull of these 4 points. However, we are not going to do it as it is typically done. We will do it using the following strategy. We'll introduce a geometric action and we'll recursively define sets. So the idea is the following. If you want to construct S1, we take any 2 points PQ in S0 and add the line segment joining P and Q to the set S1. So observe that I did not insist that P and Q need to be distinct. So you can choose P and Q to be identical. In particular, if I choose both P and Q to be this point, then the line segment joining those 2 points is the point itself, and I can add that point to the set S1. Likewise, I can do this to all these 4 points. So what this achieves is that the set Si, in this case S0, is a subset of S1 or Si plus 1. And if the points PQ are distinct, then obviously this red line, for example, represents the line segment joining the 2 points, and we can add it to the set S1. Here, the color red represents the new points that are appearing in S1 that did not exist in S0. So S1 is this particular set which joins all pairs of points. Another way to put it is that S1 is a convex linear combination of any 2 points or at most 2 points in the initial point set. Any questions at this point? Okay, so let me proceed further. We can apply the same geometric action to the set S1 to construct the next set S2. Again, remember, black lines represents points that already existed. And as I argued, by choosing P equal to Q, I can always ensure that the previous set is a subset of the new set that we are constructing. And note here that any point in the interior of these triangles can be expressed as a combination of 2 points in the previous set. So these red points get added to S2, and the black points already existed from S1. And we, at this point, we can conclude that every point in S2 is a convex linear combination of at most 4 points, that is 2 to the power 2, 4 points of the initial point set. If we continue this process and construct S3, observe that no new point was added to the set S3. It is identical to the set S2. And once this sequence has stabilized, it will remain, once it stabilizes forever. It is easy to see this property. And this stabilized set happens to be the convex hull. So the question that we can raise here is, how do we argue that this sequence that we have generated by recursive application of this geometric action on the initial point set stabilizes?
Isn't this characterizing theorem? Yeah.
Yes, thank you for that. So this is the celebrated Carathéodory's theorem that says that if we have n points in d dimensions, then any point in the interior of the convex hull of the initial point set can be expressed as a convex linear combination of d plus 1 points. So I want you to emphasize that it is independent of the number of points that exists in the initial set. It only depends on the dimension of the ambient space. And as we had concluded that Si is the convex linear combination of at most 2 to the power I initial points, it is easy to see that Si, if I is greater than this number, the sequence stabilizes. Basically, there is a logarithmic dependence on d plus 1. So what we have proven here is that as a consequence of Carathéodory's theorem, we understand that this sequence stabilizes. And any questions at this point? Okay, so now let me go on to our problem. We'll start with the same initial set. However, our geometric action is slightly different. For any 2 points PQ in the old set, we can add the line segment joining PQ to the new set if and only if the first coordinates are identical or the second coordinates are identical. Since we are working in 2 dimensions, I will succinctly represent this, this constraint as 2 points PQ being axis aligned. So if you see these 4 points, first of all, I can choose any P to be identical to Q, and 2 points, if they are identical, this condition is satisfied or they are axis aligned. So we will be able to copy every point in the old set to the new set. However, observe that if P and Q are distinct, these 2 points are only points who are axis aligned. Everyone else is not axis aligned. So the only line segment that we can add to S1 is the line segment joining these 2 points. And the new points are represented again in red. Any questions at this point? If this step is not clear, please ask questions, because everything will be just recursive application of this geometric action to the old set.
So how do you define this axis? Like there is some axis alignment.
So these are, this is actually a very good question, because the axis determines whether 2 points are axis aligned or not. So for all purposes of this talk, think of these as canonical x-axis and y-axis, like all real numbers with first coordinate 0 or second coordinate 0. This is a very good question, actually. It will show up later. So yeah, let me build on the comment that was proposed here. If you rotate the axis, none of these points are axis aligned. So you will not be able to add any new points to S1 in that case. Is this okay?
Yeah.
Then let's proceed.
Yeah.
So now, again, we can copy all old points from S1 to S2. And note that this is the only new line. These are the only 2 points, P and Q, that are axis aligned. Therefore, I can add this line to S2. Similarly, again, we can copy everything from S2 to S3. And these 2 points are the only 2 points who are axis aligned. So we are able to add this. And again, we can copy everything from S3 to S4. And every point here are axis aligned. So we are able to add this entire rectangle. Any questions at this point? The concept that the whole rectangle can be added, is that clear to everyone? Okay, so again, we can ask the natural question. The sequence that we have built by repeated application of the geometric action to the initial point set, does this sequence stabilize? So it is obvious, because I have run out of space here, that this sequence must stabilize, right? There is no further points that you can add to this set. So this is the object. This sequence is what we want to study. And the problems that we want to understand are the following. Given the initial set of points and the geometric action, can we have a succinct description of the set Si? The other question is, when, if at all, does this shape stabilize? And the other way to ask this is, does there exist a Carathéodory-like theorem for this problem? So these problems are typically known as Carathéodory, Helly, or Radon numbers for some sets. And these are very closely connected to VC dimension of sets and things like that. I will explain this later as well. Okay, so this is the new problem that we introduced. And as you can see, this is a very natural elementary problem, which I think is just as elementary as convex hulls. And surprisingly, what we had found was that this object has not been studied like explicitly. So it was an opportunity for us to name this problem something fascinating, or give this a fancy name. And in our cumulative creativity, we named it generalized convex hulls. Why is it generalized? Because if this constraint is removed, these two should be seen as a pair of linear constraints. If the dimension of this linear constraint is 0, This means this constraint does not exist, then this is identical to the problem of convex hulls. If the dimension of these two linear functionals is 1, that is the second is identical or essentially identical to the first constraint, then this problem also effectively reduces to the problem of convex hulls. And the first non-triviality occurs only when you have two independent linear equations guiding these constraints. Okay. So let me move forward and show you how similar problems have been studied in geometry and computer science. So before that, I mentioned that there is a connection between security research and geometry, which we call a wormhole that connects these seemingly very disparate fields of research. And here is the connection. So in security and information complexity, we can ask, is there a B-bit protocol for a secure computation task? And this will translate into the following problem. Does there exist, does a particular query point belong to the set SB? So if you are looking for 5-bit protocols, you will look for this point in the set S5. If this point is included, and the other way to look at it, if such a 5-bit protocol exists, can we reconstruct this protocol? Basically, we have to now find how this point exists in this set, how points were iteratively combined according to the geometric action to yield this point. And this story, or which I refer to as the generative story, translates into a secure protocol. If I want to prove that there is no 5-bit protocol, then all I need to show is that this point does not belong to S5. Further, if I want to show that any 5-bit protocol is insecure, and a lot insecure in the sense that it is constant insecure, all I need to do is to prove that the set S5 is compact in some sense. The other question is there an upper bound in terms of the size of the input-output domains on the communication complexity of computing a function? This, in fact, translates into the question whether the sequence that we generated stabilizes or not. If you have questions at this point, please ask. This is a good point to ask questions.
So in terms of this compact, so if you are starting with a finite set of points, then it always remains bounded also, right? This whole process, and it also remains closed. So.
Yes, this is a very good question. For the particular type of problems we are seeing, every SI is bounded in some sense. Yes.
And it's also, and you also always use, is there a case where I'm saying, so what's the example where it's not compact? That's what.
For the particular example that I have chosen, where you are allowed to combine only 2 points, it will remain compact. But if you are studying, for example, round complexity, you are allowed to combine multiple points simultaneously.
Okay.
In that case, this might not be compact.
Okay. Thanks.
Okay, so let me proceed further. So recently, not recently, this connection we knew earlier. So there is a connection of our problem with something known as a relativized convex hull. This convex hull is defined with respect to a surface. So let me say that a surface C parameterizes the definition of a relative convex hull. This notion of relative convex hull is somehow very similar to geodesic convex hull. I will highlight the similarities and the dissimilarities as well. Geodesic convex hulls are very popular nowadays in theoretical computer science. So for the particular problem on the geometric action that I explained earlier, let us consider this surface of formed by all points of the in the 3 dimensions formed by the following set of points. You pick arbitrary x and arbitrary y, but z is the product of x and y. So this is a hyperbola, and this is a surface in 3 dimensions. What we can do is that we can pick our point set, which were in 2 dimensions, we can lift them to this surface. And now the new geometric action allows us to join 2 points, P and Q, if and only if the line segment PQ is entirely contained in the surface that we are considering. So note that if I fix x, then this surface actually reduces to a line. It becomes, let's say if x is 5, then this becomes z equal to 5y. If I set fix y to, let's say 17, then this surface becomes z equal to 17x. So this surface into formally there is some notion of something called a family of rulings. It has two family of rulings, one that is aligned with the x-axis, another that is aligned with the y-axis. And for this particular surface that we consider, we can add the two segments PQ if and only if P1 equal to Q1 or P2 equal to Q2. Okay. So for this definition of convex hull, relative convex hull, this shape that I have shown here in green, its projection to the first two axes coincides with our definition of generalized convex hulls. So as you can understand, as you can imagine that this you can use arbitrary surface C, and geodesic convex hull basically looks at paths on the surface joining 2 points. But here we insist that you try to join them only with line segments, and you can join them if and only if they belong to the surface. Otherwise, you are not allowed to join this line segment. So in that way, it differs from geodesic hulls.
So Maji, stupid question, just confirming for myself. So you take 2 points P and Q in S0, actually in the lift of S0, right? You take 2 points,
Yes.
I'm talking about geometric action, you take points in the lift of S0 and you add the line segment to Si plus 1, which you also think of as some subset of C?
Yes, now our points have all been lifted.
Right.
S0 is on C now. It's a good question. I'm sorry, I should have clarified that I have updated S0 to lie on the surface C. And you are only adding line segments that are already on C. So the points never leave the surface.
So just to check that I'm understanding it correctly. So for a sphere, for example, there is no non-trivial convex hull.
Very good question. Yes, you are correct.
Okay, thanks.
This is a very good question. So as I always insist, there is no stupid question. There are naive questions possibly, but you are correct. These were very good questions, in fact. Is everyone clear with this perspective? Then I can proceed to another connection. Okay. Just a couple of weeks ago, our colleague Sogato was organizing a workshop on new directions in real algebraic geometry. The first day last talk, he sends me a picture of the slides that was being presented, and we are really excited. Okay, so let me tell you what was going on. So there is this real world problem, okay, that studies different partial differential equations that are solutions to, and their solutions pertaining to incompressible porous media equations. So this, let me just reduce mathematically let me state mathematically the problem that they are interested in. So they have an initial set of points, and you construct new sets of points by joining 2 points PQ which are in the old set, if and only if P minus Q, this point, belongs to some set lambda, and this parameterizes the definition of the convex hull. So for example, if we consider lambda to be the x or y axis representing the two family of rulings, then this recursive definition, in fact, is identical to the generalized convex hull that the definition of generalized convex hull that I introduced. And their objective is to understand this set S infinity, which is the union of all SIs. And they wanted to understand real algebraic properties of these sets, and this is an open research problem currently. And as you can understand, this particular special case is also open. Any questions at this point? Okay. So let me go to the computer science part of this talk. At the heart of this research lies the following problem. We are interested in determining the round and communication complexity of secure multi-party computation. Here is the model that we have. We have two parties, Alice and Bob. Alice has a private input X, Bob has a private input Y, and they want to interact with each other. And at the end of the interaction, they want to output a Z, which is drawn according to a probability distribution that depends on both X and Y. What I want to emphasize is that the probability distribution F is public knowledge. And both Alice and Bob want to agree on the same output Z. Okay. So if, for example, our objective is to sample a random coin, then we should both agree on the same outcome. We cannot have independent random coins. And we will study adversaries that are honest but curious. And the question is there a 5-bit secure protocol for a function for a function f? Here f represents the collection of all probability distribution over choices of little x and little y. And our contribution here is that we showed that this problem is in fact, first of all, decidable. This is really surprising, right? Like we didn't even know this problem was decidable or not. And I will highlight why this problem is difficult in the context of security. We also give automated algorithms that recovers the most efficient secure protocol to perform this computation. And if this secure computation is impossible, then we also demonstrate an
Excuse me, I have a question. Hello?
Yes, please.
X, Y, Z are finite sets, or they can be...
Yes, they are finite sets.
Okay, thanks.
This is a very good question. Unfortunately, in one way to look at computer science is that everything is finite, right? So here, yes, it is for ease. Let's consider X, Y, and Z to be finite and even constant size sets. Constant, like Alice has a binary input 0, 1. Bob has a binary input 0, 1. And the distribution is over 4 output alphabets. So let me contrast.
So Maji, maybe jumping ahead, are you going to consider statistical security also, since you mentioned constant?
No.
Okay, so in perfect security, right? So in some
Perfect
case, everything is constant size. Okay.
Yeah. So let me highlight why this problem, decidability of this problem is challenging. So let's think about evaluating a function correctly and not securely. Then there is an upper bound on the communication complexity of this problem. Alice can send her input to Bob. Bob can compute on behalf of Alice, obtain the answer Z, and report it back. So the total communication complexity is upper bounded by the domain size of Alice and the output domain size. However, this protocol is definitely insecure because Alice's input is revealed to Bob. And in fact, we do not know of any such canonical protocols that are also secure. There are no canonical protocols that we can use to demonstrate an upper bound on communication or round complexity of secure protocols. So it's possible that Alice and Bob keep talking forever and are unable to compute a function securely. This possibility is left open. Okay, so the previous state of the art, there is a very significant result by Chor-Kushilevitz-Beaver in 1989, where they characterized all functions with deterministic output that have secure protocols. The challenge is to consider functions with inputs that have randomized outputs. If there are functions that are that have inputs, but there is no randomized output, that is this case, we already know the answer. If there are functions without input, that have randomized output. These are essentially coin tossing, and we know how to compute all of them securely. So the non-triviality again arises when Alice and Bob both have inputs, and the output depends non-trivially on the inputs, and the output is also randomized. So to begin, let me provide some insight into how Kushilevitz characterized all secure protocols, all functions, deterministic functions that have secure protocols. As an illustrative example, I will use the auction functionality. Here, Alice has two inputs, 1 or 3, her bid, and Bob has two inputs, 2 or 4, that is his bid, and the output is the winning bid. So if we represent it by this matrix, Alice, if she bids 1 and Bob bids 2, then the winning bid is 2. If Alice bids 3 and Bob bids 2, then the winning bid is 3. If Bob bids 4, irrespective of what Alice's bid is, the outcome is 4. So for all purposes of this talk, the labels of the rows and the columns are not important. We'll just represent them using colors, and we'll just color code the output. Okay. And let me introduce how Kushilevitz plans to securely compute the auction function. So this is a very famous protocol known as the Dutch auction protocol. And let me provide some insights how this proceeds. Observe that if Bob decides to bid 4, then the winning bid is 4, and he does not find out what Alice's inputs are, and the winning bid reveals the winning bid reveals Bob's input. So Bob can go ahead and announce to the world without any reservations whether he decides to bid 4 or not. Okay, again, I emphasize we are working with adversaries who are honest but curious. They are going to follow the protocol honestly, and they are only curious to find additional information. In this model, we can ask Bob to announce whether he plans to bid 4 or not. If he bids 4, the protocol ends. If he is not bidding 4, then Alice can go ahead and announce her bid, whether it is 1, in that case, output will be 2, or her bid is 3, in this case, the bid will be 3, output will be 3. So note that in either of these two cases, the output determines and reveals Alice's input. So Alice could reveal this information without any reservation. So this is the Dutch auction where the price actually counts down and people raise hand when the first time they think that they can afford or they are willing to put down that price, bid that much amount. So the counter counts down from 4, 3, 2, and people raise their hands saying whether they are willing to pay that much or not. Okay, is everyone clear with this protocol? So, okay, so this is our starting point. And the first question that we want to ask is, can Alice speak first? For example, what if Alice reveals whether her input is in the first row of this matrix or the top row of this matrix, the bottom row or the top row of this matrix? If she does that, observe that if Bob has plans to bid 4, then Bob finds out Alice's bid. This is insecure. So what we summarize is that monochromatic regions in this matrix cannot be split. This is insecurity if you split monochromatic regions. And information theory says that if you have a secure protocol, unsplit monochromatic regions must be rectangles. So Kushilevitz characterization basically reduces to the following. Draw the matrix representing the function f, and there exists a secure protocol for f if and only if there is a monochromatic region respecting decomposition for the matrix such that all leaves are monochromatic rectangles. So the way Kushilevitz proved this is that he prophesized the outcome and proved that nothing else works. It's amazing how his intuition was so accurate. And there are lots of examples where there are no decomposition, that these functions do not have secure protocol. So he called them undecomposable functions because we have monochromatic regions, but there's no, that are rectangles, but there is no decomposition way to decompose this function. In this, this function actually has a problem of a different kind. This monochromatic rectangle, this region, blue region, is not even rectangle. So this has a different kind of an obstruction, but it's still covered by a Kushilevitz result. So now, starting from this, let us draw some inspiration from this example to come up with an approach that extends and generalizes possibly to the randomized output setting. To begin, let me introduce one of the key technical observations that we will rely in this talk. So let us assume that Alice and Bob begin with uniform and independent random inputs. So this is where Manoj's comment is important, that we are looking at perfect security, that is zero insecurity. So it does not matter whether we study this problem or the problem in which Alice and Bob can pick their inputs arbitrarily instead of randomly. So suppose we have a partial transcript tau, and Alice is the person who is supposed to send the next message. Alice can send a next message, let's say go left in the protocol tree or go right in the protocol tree. This is 1-bit message that she can send. There is a fundamental law of information theory that Alice's message cannot reveal additional information about Bob's private input. Let me elaborate on this sentence. During their prior interaction, Bob could have revealed some information about his input. What I'm saying is that this message that Alice sends is solely a function of her view thus far. So the next message that she sends cannot reveal any additional information about Bob's inputs. Information that has already been revealed, they stay, but she cannot reveal any additional information. This is basically captured by a Markov chain, which says that the next message is solely a function of Alice's view and does not depend and depends on Bob's view through Alice's view. As a consequence of Markov constraint, we can conclude that the marginal distribution of Bob's inputs conditioned on a partial transcript does not change. Let me elaborate on this further. Suppose I know the marginal distribution of Bob's inputs conditioned on the transcript being tau L. And rho tau represents the marginal distribution of Bob's input conditioned on the transcript being tau. What we are claiming is that this distribution must be identical to this. This distribution must be identical to this. So these two distributions are in fact identical. This is a fundamental law of information theory. What I want to emphasize is that there is no way to finagle around this law. There is no approximate version of this law. Alice cannot reveal a little bit of about Bob's. No, that's not possible in information theory. This is a fact of life. You have to live with it. Any questions about this slide? This is very crucial for whatever we are going to talk about next.
Question I have, reveal to who?
Sorry, can you repeat that?
Reveal to who? It's revealing, but revealing to someone, right? So Alice cannot reveal to Bob to its own key, private information. Is there a third person involved? I mean, I am not in cryptography, so I just please.
So this is a good question. I should elaborate like condition on the public transcript. See, the definition is marginal distribution of this condition on the transcript. Someone, an eavesdropper who is looking at the transcript.
Okay, got it. Yeah.
That's a good question. Actually, I should have emphasized that more. But if you see, like I try to put that, or let me put it this way, I try to cram it into the definition itself. That's a good question. Thank you. Okay, so what I'm going to say next is that these two partial transcripts, I'm going to refer to them as siblings because they have Bob marginal distributions that are identical. And Alice is bonding these two siblings. So here is our new narrative for secure computation. What I want to emphasize is that it's a bottom-up narrative. Recall Kushilevitz protocol, it went top down. Our new narrative is bottom up, and we will define it using bonding among siblings. Okay, so keep an eye out for these two words. What is bonding and what is sibling? Okay, so to begin, let us imagine what protocols we can compute without any communication. These are constant protocols, protocols that have constant output. So at the end of the protocol, we know that the function that we are computing are constants. So either the output is already known to be 3, 2, or 4. If the output is 3, then we definitely know that Alice's input is top row and Bob's input is the left column. If you know that the output is 2, then we know that Alice's input is the bottom row and Bob's input is the left column. If we know that the output is 4, then we are certain that Bob's input is the right column and Alice's input may be the top row or the bottom row. Security implies that both of these inputs should be equally likely. That is, the conditional distribution of Alice input conditioned on the partial transcript must be half-half. So these informations are represented in this figure. And now the question that we ask, can we find siblings? Note that Bob distribution here is identical to the Bob distribution here. So these two, in fact, are siblings, and we can bond them into a new protocol for a function that computes a part of the original function. Here, we are certain that Bob's input is the left column, but Alice's inputs are equally likely to be the top row or the bottom row. So this new matrix requires 1 bit of communication to be securely computed. That's the intuition. Is this clear? So now we have this bag of new functions, and now let's search for more siblings. Note that Alice marginal distribution here is identical to Alice marginal distribution here, and we can bond them together into this new function, or the final function that we are interested in computing, where Alice's inputs are Alice's input being bottom row or the top row are equally likely, and Bob input being the left column or the right column are also equally likely. So we have reinvented Kushilevitz protocol in a different manner. Our narrative is bottom up, and we define it using bonding of siblings instead of Kushilevitz narrative, which was top down and relied on decomposing the function. Okay? Any questions at this point?
The bonding idea here, is it a throwback to the geometric picture that you showed us earlier?
Yes, it's actually this is the same picture. Yeah, this is through. Does not correspond to that picture exactly. I have an example randomized output function that corresponds to that picture. I will not be able to cover it in today's talk, but I can give you the slides. You can distribute it freely.
But Maji, I think the question is, so here you combine them half-half, but all convex combinations are good, right?
Oh, yes. That's a good question, actually. All convex combinations are good. I'm illustrating only the half-half combination. So these two can be combined in arbitrary lambda 1 minus lambda combinations. Okay, so the natural question is, I never told you whether bonding two siblings is secure. Maybe all this will fall apart if bonding two siblings turns out to be insecure. So we proved that actually bonding any two siblings are in fact secure. So that is our one of our technical contributions. And if you can, if you go back to what I had talked about undecomposability from Kushlevitz's perspective, our reimagination states that basically these are unbondable. No two pieces here could be bonded, and here also these two pieces cannot be bonded. And what is our new perspective on security? Our new perspective on the security says that a protocol must be secure at the end, and it must respect the Markov law. What I want to emphasize is that this definition, security only exists in the first part. The second part is independent of security definition. It's a law of nature, and it's a geometric action. This basically translates into a geometric action, which is independent of the notion of security. Only the initial set of points encode security. So you can change your notion of security, and this the definition of this narrative of security still extends to that. And the other thing I want to emphasize is suppose you are interested in investigating statistical forms of security. This must be encoded here. There is Markov law does not have an approximate law. Alice cannot reveal partial information about Bob's input. That is not possible. There is no finagling around this law of nature. This law is perfect. Another technical insight that we had was that these constraints that I explained using English can be entirely encoded using geometry. And here is the high-level overview. We can encode this as points in high dimensions, where the first few coordinates encode Alice's marginal distribution, next few coordinates encode Bob's marginal distribution, and the remaining coordinates encode the function. And we can convex combine 2 points if and only if the marginal distribution for Alice A and A prime are identical, or the marginal distributions B or B prime are identical. That's why we are considering linear constraints. That is, and there are 2 independent constraints. So we start with base case, which encodes all 0 round computable functions, and we geometrically apply this action on to construct more complex sets. These represent protocols that require more communication complexity. And our target is a point which has uniform Alice distribution over Alice inputs and uniform distribution over Bob inputs, and encodes the target function f. And we are interested in finding whether this query point Q belongs to this set SB. If yes, then there is a protocol for f in using B bits of communication, and the parse tree of how the base cases generated this query point translates into a secure protocol. Finally, if this point, if this point is not in this set, then there is no secure protocol.
So, Maji, so the
yes.
question. So the this uniform distribution, as you said, is arbitrary. You could have used any distribution, right? With for support,
Yes,
any product distribution. So is it is it obvious to see that if QF with the uniform distribution is in the set, then so would be the other ones, because they have to be.
It's a very beautiful question. It actually says that our picture could be stretched along x-axis or y-axis, and the picture essentially remains unchanged.
So is that something you would be able to show without appealing to security? Like, is that?
Without appealing to security, we can prove this just by geometry.
Okay.
Because you can just stretch the fabric of x and y axis, and it's still the laws remain the same. It's a very good question, actually.
Hello. Can I ask another question? Yeah.
Yes,
so
please.
you colors, do they represent one deterministic output or distribution of output? Like
here it is deterministic
functions. Now it's a probabilistic function.
No, it isn't. I have not shown you the probabilistic function yet. I do not have the time for that. I just wanted to introduce this new narrative that is a new generalization or reimagination of a classical result where outputs are deterministic.
Got it. Then
I will share the slides. There is an example, worked out example with lots of nice animation. You can go over it.
So,
okay.
Maji, so even when you're working with distributions, isn't the kind of the dimensions doesn't it correspond to the alphabet, the finite alphabet of the output space?
This is a very good question. The ambient dimension corresponds to size of x plus size of y plus size of z. The initial number of points corresponds to number of output, that is size of z.
Right, Z is a finite alphabet, right? Like it's a
finite alphabet.
Yeah,
yes, okay. It's very important. It is finite.
One more question. So everything you said is in terms of symmetric functions. Both parties are getting the same output. Do
Yes.
things generalize to different outputs for the two parties?
We proved it, right? Like these questions all reduced to, there is one more bit. In that there is a little bit more communication.
And in the deterministic world, we did this, right?
Yeah.
Not just us. I mean, there
was randomized also. We did it, right? We had this notion of connected components and things like that.
And that's for completeness, but for the basic feasibility, we don't know, right?
I think it should not be a problem.
But right now, you have not worked it out for the general.
No. Okay. For me, that is the okay. There are much more interesting problems that I want to present.
Sure.
Yes. I don't think that there are any technical challenges. As I presented, the notion of security is not important. It's only in the base. It's encoded in the base set. Okay, so have we seen such connections between two very disparate, seemingly disparate sciences earlier? In fact, yes. There are works that have connected distributed problems in distributed computing, their problems relating to their decidability, and to topology research. However, one fascinating thing about our research is that the new problems that we generate in geometry remain open, while in their case, the topology parts were already answered and they build a bridge to bring those answers to the setting of deterministic computation over distributed among multiple parties. Let me quickly go to the conclusion. So this is basically is the protocol corresponding to a function that has randomized output. I will share the slides. You can look at it at your own leisure. Let me talk about some of the recent progress that we have on this problem. So as I asked whether this problem stabilizes or not, what we can prove is that there is a set of points in 3 dimensions such that the initial set of points has only 5, and this the sequence that we generated never stabilizes. So what does this mean? This means that there is a function that has binary input. Alice has only 2 bits as inputs. Bob has another bit as input. And the output is a probability distribution over 5 outputs. And it has no perfectly secure protocol. It only has statistically secure protocol. So this result actually is a counterexample and falsifies a widely believed folklore that suggested that there should be an upper bound on computing any function securely. That depends. The bound depends only on the size of the input-output domains of the parties. In fact, it's a very strong result. It basically says that there are some functions that have statistically secure protocol, but no perfectly secure protocol. Intuitively, there is no error correction possible for these secure protocols. However, both these conjectures were true for functions that have deterministic output. It's amazing. Like, you can compute this function with arbitrary precision, but you can never compute it exactly. However, contrast this situation with communication complexity. Every function can be computed precisely within using round complexity or communication complexity that depends only on their input-output domain size.
So is it so is this really dependent upon the range being R rather than Q?
No, actually, our counterexample only uses rational numbers, nice rational numbers. The description complexity is also small. They are multiples of 1 by 32.
But then arbitrary, I mean, like if I get, so if they're 1 by 32, then
Sorry. Arbitrary, okay, sorry. What I meant was that, okay, let me be more precise. You are correct. Arbitrary precision is obviously, it will be exhaustive. The ith set is uses numbers that are whose denominators are 32 to the power I.
Okay.
Yeah. So it's if you fix I, that's the way we'll think about the problem. It is arbitrary. It is fixed precision.
Okay.
So let me conclude with some of the problems that we are currently working. Does this sequence converge? Our conjecture is yes. Can we compute the limit set? Yes. And the technical ingredient to solve this problem has led us to a fascinating journey. And it basically involves solving system of containment inequalities over the polyhedral semiring. So for example, when we write inequalities x greater than equal to y, we use real numbers to show that x is greater than equal to y, right? But here we are working with convex polyhedra. So x is a convex shape, y is a convex shape, and x is greater than equal to y if y is contained inside x. And this has led us to actually led us to new research in tropical algebra. Maybe we can call this MPC on the tropics. And with that, I want to conclude my talk. I again thank my co-author and colleague Sogato for leading me into this fascinating world of mathematics. And my students, Hamid Raza and Hai. By the way, these two students were central and to proving that the sequence does not converge. Because Sogato and I, we were trying to prove that these sequences converge. And they did not believe us. They came up with the counterexample. And I also want to thank all the funding agencies who helped me study this problem over multiple years. And with that, I want to conclude the talk. If you have any additional question, I'm sorry I overshot the time limit allocated. If you have questions, please let me know. I will also make the slides freely available.
So again, to go back to that round complexity, so the round complexity increased with the precision, is that the so as you
yes.
Maji, you said that like I mean this bad is 0, which does not stabilize. Oh yeah, this slide. So you are able to find this bad as S0 in R3, right? So I mean
in R3.
In R3. So is there like a possibility? Like, does there exist a bad S0 in R2, or is it trivially?
No.
Okay. Right.
That's a good question. I think we can prove that it does not. Yes, we can prove it. Proof is non-trivial, by the way. We can prove that it stabilizes in order n square steps, where n is the size of the initial set.
I see.
This result is non-trivial. By the way, the proof of this result subsumes to the result that I alluded to while answering Manoj, that if you stretch the fabric in x or y direction, you do not need to stretch it uniformly. You can stretch a little bit part, compress a little bit, stretch another by a different amount. You can do all these things, but the picture essentially remains the same. There are ways to define linear maps under which I think it's the technical term is trivializes. The shape trivializes along those directions.
Any other questions?
So the fabric thing that you were saying, it doesn't have to do anything with the security. It is the basic, the information in the Markov inequality, which is playing in there. I didn't quite understand.
It is even more fundamental. It has to do only with geometry.
Okay.
the constraint that you can only add 2 points which are axis aligned. It just uses that
Okay.
fact.
Okay.
So I have
So
to confess, I did
before
not.
I conclude, I just want to put this out. There is a big possibility that we will be able to formulate our problem as a incompressible fluid problem, and maybe the stationary solutions of those physical problems correspond to secure protocols in cryptography. So for the first time, we might be able to have something physical, some tangible things that actually correspond to secure protocols. So
That
yeah,
sounds
we are
like
also
great
looking
news.
into that. Like we have not been able to entirely make that whole connection back to the, bring that back to the physical world.
Okay. So yeah, that will be great because, Maji, I know you've been working even when you were a student, this is a problem you've been working on for a
If I
long
remember
time.
correctly, this was the first problem you gave me.
This were one of the initial things we started with. Of course, we did have some progress to show for that, and you managed to graduate at that time.
Yes,
But,
you have a result with Data Prabhakaran paper, right? Which worked with
yeah.
3 outputs.
Yes, so
Basically,
you
showed the
can
3 output.
rederive those results, right? I believe.
Yes, we can rederive this. So interestingly, that you defined a notion of equivalence, that 2 outputs are equivalent if their ratios are identical in some sense. This actually corresponds to our setting that the 2 points happen to be coincident.
Okay.
So effectively, there will be only 3 points on the yeah.
Well, yeah, I'm sure we are not done with this. I'll get back to you with more questions later on.
Yes,
But
definitely.
since we are running out of time, I think we'll thank you. And yeah.
And thanks for having me.
Sure, our pleasure. Yeah, good.
Yeah, I have not been to IT Bombay for a very long time, actually. Like
You should visit us. Yeah, let's know next time you are around. We'll
That's
have you
beautiful.
fly over here.